Now, when we defined unions and intersections, we defined them on two sets only. So A union B, or C intersect D. Now, what if you had a whole bunch of sets, maybe a billion sets that you wanted to take the intersection of or the union of? Well, by the associative law, we didn't have to worry about brackets. So if you had A union B, union C, union D, and so forth, we could first take A and B and union them together, and then take C and union that onto A and B, and then D as well. And that's fine, but we could have done it in any other order as well, which means that we don't actually need to write the brackets when we're doing these operations. And that's a very useful comment and observation, because that means that we can take any number of sets and take the union of them in one big go without worrying about the order of which ones we're now unioning on. Now, if you do have a billion sets, you might not want to write them down if you're writing the union of them, you know, A1, A2, etc., up to AN. Now, there are two ways of simplifying that notation. Instead of writing all of those up, there's this notation here, which is just to write the first set, union the second set, etc., and then three little dots which say, I'm too lazy to write those intermediate things up, but I hope that you, dear reader, knows what I'm talking about. And similarly, we can say one set here intersects another set there, intersect, ... I'm too lazy, please fill in the trivial details, dear reader. Intersect the last one, AN, where n is some possibly given number. It could be a billion, or it could be undefined, just n, for instance. Now, here I've labelled the sets A1, A2, etc. up to AN, because there's the second way that I alluded to just before of writing up such intersections and unions, which is this notation here, the generalized set operation, union here and intersection there. So this notation here is just a very compact and useful way of writing up this expression there, which in turn is a nice and compact way of writing up possibly very large union of sets. So let's have some examples. So for instance, if these sets here were defined slightly implicitly in this way. So whenever we have an integer k, we define it to be just the numbers k and k plus 1. So now if we're just to have a very simple example where it might not even make too much sense to use this notation, but let's just use it anyway just to show how it works. Then we could look at the the union of these AKs, where k then goes from 1 to, let's say, 3. Now here I've got k and I. They are two different things. So this expression there doesn't look quite like this. Here we've got n being equal to 3, so we've used a different symbol, but it's basically the same thing. This is just a special case where we put n equal to 3. Here, whether we call the index I here I, or we call it k, it makes no difference. The principle is going to be the same. Namely that if we look at this, it's going to be the same sort of thing as here. A k, where k goes from 1 to 3. So we've got A1, and then we're unioning everything. So k goes from 1 to 3, so the next one is 2. And finally we have where k is equal to 3. There are no little 3 dots there because we've got so few sets already, so it doesn't make sense to write any dots. What's that equal to? Well, let's just wait 1 second to find out what that is equal to, and look at the corresponding generalized intersection operation, which is this one here. So if we use exactly the same expression, but just write intersection here instead of union, then we have that this would be A1 intersect A2 intersect A3. So here again, k goes from 1 to 3, and for every one of those 1, 2, 3 values of k, we then take ak being equal to A1, A2, A3, and we're intersecting everything. So these two expressions are equal to these two expressions. But what are they actually equal to? What are the sets that we're talking about? And here we have some sets given, so let's figure out what A1, 2 and 3 are equal to. And we can do that over here. A1 is then equal to, well, here k is equal to 1, so we've got k to be 1, and 1 plus 1 is 2, so that's the set 1 and 2. Here we've got A2 being equal to the set 2 and 3, and finally A3 is equal to the set 3 and 4. Okay, so if we want to if we want to look at the union of these three sets, then it's everything that's in the set, which is 1, 2, 2, 3, 3, 4. In other words, it's the elements 1, 2, 3, 4. We, as usual with sets, ignore any duplicates, and that's the union of these three sets there. And you could, of course, change that 3 to a 17, and then you'd get the numbers from 1 to 17 plus 1, which would be 18, and so forth. So this example is quite simple. Sometimes it's not as simple, and you might see that in tests or exams. But it's generally an easy exercise to do if you bump into those sort of exercises. Down here with the intersection, what do we have here? We've got the sets 1, 2, 2, 3, 3, 4, and we're looking at the intersection of all of these in one go. You could do them pairwise, the intersections, but we could also ask it in a different way, a more simple way, and say, this set here, or that set there, is the set of all the elements that are in all of those sets at once. And if we look at these, well, we've got 1 and 2 in this set, and there are no 1s and 2 there, so we won't have any element which is in both A1 and A3 at the same time. So the intersection of A1 and 3 is empty. And if you keep intersecting it with A2, it'll still be empty. So we have that this is the empty set. There are no elements that are in both 1 and 2 and 3 at the same time. So that's the empty set. So that's how we can generalize our notion of union and intersection using some notation, either this very compact form or this relatively compact form. So let's look at an exercise dealing with these generalized intersection and union operations. In particular, we'll be looking at these sets and looking at these unions and intersections here. We have to find them, but please pause the video, try to find them yourself, and I'll give you a bit of time to pause the video. Okay, so let's have a look at these. We've got to look at these sets there and take the union of the sets that are given here using this notation, and then the intersections of these sets given here. Now, what sets are we dealing with? We've got AK, where K goes from 2, 3, all the way up to 4. So we're talking about the three sets. A2, where K is 2, union with A3, and finally union with A4. That's equal to something, whatever it is. Down here we have the intersection of AK being equal to 3, then 4, then 5, then 6. So let's write that up there. A3 intersect with A4, intersect with A5, intersect with A6. And that's also equal to something. Now, in order to figure out what those somethings are, what those two sets are, we really need to have a closer look at what these sets actually are equal to for different values of k. The k values that we're looking at are 2, 3, 4, 5 and 6, so let's quickly have a look at them. So A2 is equal to, well, what is that equal to? It's a natural number, so in this course it's any number from 0, 1 and upwards. In general it could be 1, 2, and there's a bit of notational convention. Either people write n, meaning we're starting at 1, 2, etc., or we're starting at 0. Here in this course we're starting at 0, so these are all the numbers, the natural numbers, 0, 1, 2 and so forth, that satisfy this condition here, that lie between k and k squared. Here k is equal to 2, so here we're saying these are all the natural numbers that lie from 2 up to 2 squared. So we're talking about 2, 3 and 2 squared, which is 4. So that's the first set there. And then we can find the other sets, A3 being equal to all the natural numbers from 3 up to 3 squared, which is 9. So we could say 3, 4, dot, 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 meaning I'm too lazy to write the remaining the remaining elements up there, but hope that you, dear viewer, dear reader, if we're writing some text, can fill in yourself. A4, we've got all the numbers from 4 up to 4 squared, which is 16. And there's an extra dot. Let's rectify that quickly. 5, 6, and up to 25. They are the numbers that are the elements of A6, A5, and finally A6. We've got 6, 7, and all the way up to 36 being the elements of A6. So they are the sets that we're looking at right there, and we then can just look at the union of A, 2, 3, and 4 and basically just write down what the answer is. We're not always going to be that lucky in these sort of exercises, but here it's straightforward. So we are dealing with A, 2, 3, and 4. So these numbers, union with these numbers, with union with these numbers. So basically all of the numbers that we see there, 2, 3, 4, 4, 3, 4 up to 9, 4, 5 up to 16. So they all overlap. So it's all the numbers from 2, 3, and all the way up to 16. So 2, 3, 16. If you are doing such a problem like this in a test or exam, you don't need to give much in the way of explanation. If you write down like I have and write the sets up, then you should get mostly total full marks, even if you make a mistake or two. So what about the intersections here? A3, 4, 5, and 6. So we have A3, 4, 5, and 6, and we're supposed to look at the intersection between each of them. So let's see what numbers are in all of them at the same time. And you see that we don't have any numbers that are bigger than 9, or any numbers that are smaller than 3, or in fact smaller than 6. So A6 doesn't contain 3, 4, or 5, but it contains numbers bigger than 9, so we have to discard them as well. So you can sort of see here there's a sort of a diagonal pattern going on that separates here, and 8 and 9 are getting a bit messy here. But sort of if you visualize it a little bit like that, we see that 6 is the first number that is in all of these 4 at the same time. Then we have 7, 8, and 9. They are also. But once we get to 10, well, 10 is in each of these sets, but not in the first one. So it's not in the intersection of them all. So the intersection here is just these numbers here, 6, 7, 8, 9, and we are done. 6, 7, 8, and 9. And once again, you don't need to write an essay or even write any sort of description as to how you got that answer. As long as you've written up all of this, that should be perfectly sufficient.